Hi everyone, thank you for joining our talk today. In this talk, you will learn about MLPerf and how it runs on Kubernetes. This is me, Elvira Dzhuraeva. I'm a technical product manager from Cisco, and we have another speaker today, Xinyuan Huang, and he is a technical leader at Cisco. So let's get started. In today's agenda, we will cover some general information about benchmarking and AI, some introduction into MLPerf community, and Xinyuan will talk about MLPerf in details about trainings and inferencing and other benchmarking. Also, we'll cover how to run MLPerf on Kubernetes. In this slide, you can see the huge picture of variety of tools for big data and AI. This landscape shows how much AI was integrated into our lives and how many tools we can use nowadays to support our machine learning applications. And given this amount of platforms and tools and infrastructure and even hardware, how do we know that we run our machine learning workloads in the most efficient way? And how can we compare our results and our efficiency? And this diagram was prepared by Matt Turk, and he always creates these kind of infographics each year to showcase the industry. As I said, given the amount of tools we have, how do we know what to choose? And especially when it comes to performance, how do we know which direction to choose and what thing you need to look in first in order to improve it? Do you need to improve your network? Do you need to improve your hardware accelerators? Or maybe something wrong with the model code? So which direction to choose in order to achieve the biggest impact? So benchmarking is the answer to that. So benchmarking helps to answer the questions like, how efficient are the leading companies in their niche? Why are they more efficient? And what steps we need to take to improve effectiveness across all areas of our business, including machine learning workloads? And as well as how can we use this benchmark to improve our next year's evaluation and our technology improvements for the next year. So, as I said, we have so many technologies, and because of the complicated nature of machine learning workloads and infrastructure behind it, as well as the models are so different from one another. So how can we compare the effectiveness and performance if these tools are not even close to each other? And we use benchmark in AI to achieve this efficiency and effectiveness, improve the performance potential. And through that, we can even expand our business horizons. And it will help to motivate our staff because they will see the area where they can improve the current infrastructure. And it can boost the innovation and inspiration in order to achieve the best results. And it will give insight into the present performance and save potentially operation expenses. So I'm going to introduce MLPerf. It is a fair and useful benchmark for measuring training and inference performance of machine learning hardware, software, and services. So MLPerf was created by a large community. We have more than 60 organizations and 8+ universities and more than 1,000 members in this community contributing to this machine learning performance standards. You can see like very huge and big enterprise companies such as Google, Cisco, Microsoft, HP, and many others contributing to it, as well as very prominent universities such as Harvard, Stanford, University of Toronto, that all these communities are heavily working on the one set of benchmarking that can be used across the industry. So anyone can use these benchmarks and can compare its machine learning performance both for the inferencing side and the training side. And based on this comparison, you can make the insightful and informed decisions based on which direction to go and improve your performance and effectiveness, as well as save the operational and business costs. And now I'd like to hand it over to Xinyuan, who can talk more about MLPerf benchmarks, as well as how MLPerf can be used on top of Kubernetes, because Kubernetes currently is one of the most leading platforms across the industry that can be run both on premises and in the cloud. So opening MLPerf to Kubernetes, meaning that you can expand your benchmarking to the highest and standard level. So please, Xinyuan.
Okay. Thank you, Elvira. This is Xinyuan, and I am going to start with a brief introduction of MLPerf benchmarks. So, in the last few years, there has been a lot of efforts put in the benchmark development for machine learning systems. And earlier works in the field starts with micro benchmarks, such like deep bench, that isolates and evaluates individual operators in a machine learning workload. Well, this approach is useful for evaluating individual components or aspects of a machine learning system. People quickly realized that micro benchmarks cannot reflect the complexity and challenges in a real-world system. So in order to address this problem, people gradually moved to use workloads that are at real-world scale and start to evaluate an system from end to end. So, for example, TBD and downbench are some of the outstanding works that takes those approaches. And MLPerf is one of the latest efforts in this field. MLPerf is built on strength of its predecessors, where it tries to combine a broad set of real-world benchmark workloads along with end-to-end metrics that evaluate the software and hardware stacks as a whole. MLPerf is also inspired by the industrial consortium such like SPEC, where the benchmarks are developed and maintained by a broader organizational effort and then embraced by the respective communities. Okay, so I apologize for the delay, and we have technical issues here, but let me resume my presentation. The most important goal of MLPerf is to enable a fair and useful benchmark. That means it needs to reflect real-world challenges in ML systems performance by using models and data at a real-world scale. MLPerf also strives to make the benchmark results reliable by putting in a large amount of effort in rule designs that enforces reproducibility. And finally, MLPerf wants to be designed in a way so that it can encourage state-of-the-art innovations in both research and commercial communities. The MLPerf benchmarks today consists of two main tracks that are training and inference. These target the two most important tasks in ML lifecycle. And now let's take a brief look into each of them. MLPerf training track provides 8 workloads today that cover a number of popular fields and typical machine learning tasks, which includes image classification, object detection, translation, language modeling, recommendation systems, and reinforcement learning systems. And by the way, I just want to clarify that the list of workloads here is by no means a fixed list, and the MLPerf community will keep adding more new workloads as new developments in the machine learning community become mainstream and come into our considerations. The main approach we take to measure performance in machine learning training is to train a model from scratch to a target quality and measure the total time taken in the time training. This is a very computationally expensive approach, and there must be questions that why don't you use simpler metrics such like throughput? Or the answer is that although more affordable approaches such like throughput can give you a performance number at a given time point, it doesn't necessarily reflect the overall cost of training in the real world. So let me give you an example. One important observation here is that you might be able to easily increase the throughput of a machine learning system by increasing the mini batch sizes in training iterations. However, there is a side effect which is often overlooked, that in some cases, or in most cases actually, increasing batch sizes will have a mathematical impact to your optimization process that will cause your model to converge slower. And you might end up training a model for more epochs to reach the same quality, which means that you might have a higher total cost for your training job when you train at a higher throughput. So comparatively, end-to-end training time is a relatively better measurement in a way that it targets the total cost of your whole training process instead of instant performance. And that also encourages the system developers to optimize their systems in the right direction. Now let's take a look at the inference track. As of today, the inference track provides 5 workloads that includes 2 image classification tasks, 2 object detection tasks, and a translation task. And more workloads are being developed at the moment, and they are going to be added soon in the next release. Similar as training, MLPerf inference tries to design a realistic set of metrics for performance measurement. The overall idea here is to use both quality and performance for the measurement, so that you do not, over-compromise quality of service to achieve a marginal improvement in performance, and vice versa. In the inference world, there is a wide range of different use cases and different systems that range from clouds and data centers to edge and mobile devices. The requirements for all those systems and use cases are largely different from each other, and hence we need to evaluate them under different scenarios. In MLPerf, there are 4 types of scenarios today. The single stream scenario targets those use cases where inference queries come in at a constant rate and a single sample at a time. This is a case very commonly seen in things like video processing applications, especially in the edge devices such like phones and cameras. The performance measurement of this scenario is to simply measure the latency of each query. The multi-stream scenario is similar as the single stream in a way that it also involves inference queries that comes in a streaming manner at constant rate. However, in this case, it involves multiple streams of data at the same time, and an example case is that, say, in an autonomous driving use case, where many sensors data are injected into an inference engine at the same time, and they need to be processed altogether in parallel. The measurement of multi-stream scenario is to measure the maximum number of streams possible under the condition that the latencies can be guaranteed under a certain threshold. Now there is the third scenario, that is the server scenario, which is mostly suitable for machine learning applications as an online service. For example, recommendation services and translation applications are some of the popular use cases. In this scenario, we issue queries at an arrival rate that follows Poisson distribution, which mimics the inference queries in real world. Then we measure the performance by setting a latency threshold first, then measure the highest QPS the system can reach on the condition that the predetermined latency threshold can be met. This can reflect the real-world requirements where you want to optimize your system performance while still meet a quality of service requirement. And finally, there is an offline scenario which is also mostly suitable for a server-based system. It is suitable for applications that do not care about latency and requires to process a large batch of data at the same time. So in this scenario, data are grouped into a large batches and sent to a target system all at once. And the performance is measured using throughput numbers. So now we have very briefly walked through the basics about MLPerf benchmarks. We want to talk about Kubernetes. As you know, the MLPerf benchmarks are designed for evaluating the whole software and hardware stack of a machine learning system, and Kubernetes can certainly take a part of such a system. So we want to see how we can run MLPerf on Kubernetes, and more importantly, how we can leverage MLPerf to optimize the machine learning performance on a Kubernetes-based machine learning system. So first of all, let's look at training. The training workload itself has no difference between running on a bare metal environment and running on a Kubernetes cluster. The main difference comes in the orchestration part, where you turn the model training program into a Kubernetes job. And also the setup of shared hardware resources such as accelerators, network devices, and storage devices that are now managed and allocated by Kubernetes. So here are a few things that we want to take into consideration if we want to maximize the performance when adapting to MLPerf training workload on Kubernetes. So first of all, to run training at real-world scale, you might need help from some distributed computing libraries or frameworks, such like OpenMPI or Horobot or distributed TensorFlow, etc. You might want to take some extra care when deploying programs using those frameworks on the Kubernetes cluster. And luckily, the support for those distributed training do exist in Kubernetes community. For example, you can check out powerful tools such like Kubeflow or other similar works that can help you simplify the deployment of distributed training jobs on Kubernetes. And talking about distributed training, another important problem we want to address is the resource scheduling. Now that all the compute and network and storage devices are managed by Kubernetes, to maximize performance, you want to make sure that you have the right affinity settings that co-locates your Kubernetes resources. So here we also want to talk a bit about topology management. That can be considered as another kind of scheduling in a more micro scale. The topology management we are talking here is basically managing the alignment of CPUs and peripheral devices, such like GPUs and NICs within the NUMA system, so that you will get the best performance when you correctly align the CPUs and peripherals to the same local memory in a given worker node. And also, we do see that there's a better feature for topology management in latest Kubernetes release. So this is going to be very helpful for us to leverage the NUMA system. So in addition to the problems related with distributed training, there are also other settings you might want to take care. You want to have the proper plugins for compute and network devices, such like GPUs and NICs. And you might also want to set up corresponding CNI plugins for your SRIOV network devices so that you can get support for high-performance network communications. And this is also very important because the default network setup in a vanilla Kubernetes cluster is not going to be an optimal choice for intensive workload like distributed ML training. And finally, there are a few other aspects which might also make some differences. One of them can be the performance of your volume access, and others can be some security policy settings that might give you extra privilege to access host resources directly. So these are the main factors we consider for running and optimizing MLPerf training workload on Kubernetes. And now we talk a bit about inference. There might be two ways that you can use to run an inference performance test on a Kubernetes cluster. One of the ways can be to run it like a local job where you only test the performance of the parts specific to the machine learning task. And this is the default method also as specified in the official MLPerf rules. So let's first take a look at how this would work. MLPerf inference provides a load generator that works like a harness for benchmark experiments. During a benchmark experiment, the load generator will first query the system under test, or we call it SUT, to load a portion of test data that fits into its memory. The SUT loads the query data with help of a data module and then returns to the load generator with a ready signal. Then the load gen will start issuing inference queries at a given distribution where the SUT will be responsible to pass the queries to the backend inference runner where the inference results will be get. The load gen will be able to log the outputs afterwards, and then finally a post-processing script will be used to process the outputs and get the summarized report. So as you can see, all this process is happening in a local device where the inference queries and outputs are all simply transferred from memory to memory. This is an ideal way to test your performance when you want to eliminate all other factors that are non-relevant to the inference task itself. However, now in a Kubernetes environment, it is very common to run a machine learning application as a service. For example, you might be leveraging some inference services such like KF serving or Seldon, or you might be simply running a TF server to serve your machine learning models on Kubernetes. And you might also want to be interested to know that what is the end-to-end cost of your inference service from a client point of view. And in order to do that, we will need to make some modification to the original mechanism as defined in MLPerf. So in this case, we will load and serve a model in a remote machine learning service running on Kubernetes, instead of directly on a local SUT. Then we can implement the SUT as a client that is able to query such a Kubernetes service as its backend. In this way, we will be able to get the end-to-end service level performance evaluation from this modified SUT, while we will still be able to leverage the special load gen behavior from MLPerf. So finally, we want to show some example performance results from a very simple, very small experiment we did. Before we go into details, I just want to clarify that the experiment settings and the target requirements are all fitted to our specific testing environment and are not directly aligned with MLPerf's official rules. So please just take it as just a demonstration only, and do not compare it with official MLPerf results. In this experiment, we took the SSD mobile net workload and ran it on a vanilla Kubernetes cluster that uses default network setup and uses CPUs only for the inference. The experiments are done on 3 scenarios, which are single stream, server, and offline. And we compared the results from the 2 experiment settings we talked about just now. One of them being the machine learning only test, which uses TensorFlow locally, and another of them is the end-to-end service level test that uses TF serving to serve a model in the Kubernetes cluster and use the client side to query it. From the charts, we can see that there is maybe 10 to 15% difference between the 2 settings, and both in the single stream latency and in the server's QPS numbers. And the delta is even a bit larger in the offline throughput. So after some further investigations, we find that a large portion of the extra overhead might come from the network communication. And if we use, say, GPUs instead of CPUs, the inference time might be further reduced, which means, on the other hand, it can make the extra overhead even more significant. So in this example case, we would want to improve our software stack in the corresponding part so that we can improve the service level performance, especially on the network communication side. Although I would say that it might be controversial whether some of the overhead in the end-to-end experiments would actually make sense from the perspective of a pure machine learning benchmark. But I think that this would at least help us to get some ideas or point us to some directions where we can know how we can optimize our machine learning system that is built on top of Kubernetes. So if you are interested to know a bit more details about this example, or if you want to try it on yourself, you can go to the repository that is shown on the slide, where you will find some additional details. So that concludes our presentation, and I would like to thank you for your attendance. And if you are interested to learn more about MLPerf, you can go to the MLPerf.org website to learn more details. And please feel free to contact us if you have any questions. Okay, thank you very much.
Thank you. So now we have some time for questions and answers. And if you have any questions, please feel free to ask them now, and we will try to cover them. seems like we don't have any questions. So then thank you very much again for coming and hearing this talk. And if you get some additional things, please still feel free to connect us via email. So thank you very much again, and thank you. Bye-bye.